We all have seen the visuals of an autonomous car driving on a road without a driver. It navigates through the lanes and cars without crashing. Isn't it fascinating? Hello everyone, I Aditya Nisar, along with my colleagues Prathamesh, Tanish and Anshul, will present before you our deep learning project on implementing a feature pyramid network with panoptic segmentation, traffic object detection, which is an addition to the ongoing research. So without wasting any further time, let's dive in. The agenda for our today's presentation will be the introduction and project motivation. We'll be touching the project aim, review of existing research. We'll be going through the data set and the challenges that we face with the data set. We'll also discuss our work and methodology, the model selection, the hyperparameters and performance metrics. Then we'll conclude with the results and the comparisons, and we'll then go through the conclusions and questions. Talking about the project motivation, FPN is a popular architecture for capturing multi-scale contextual information. It has been shown to improve the object detection performance in several state-of-the-art models. By incorporating FPN into YOLO-B, we expect to achieve a significant improvement in the model's accuracy and performance for panoptic driving perception tasks, which can have a practical implications in the development of safer and more reliable autonomous driving systems. So moving on to our aim. Our main goal is to implement FPN with panoptic segmentation. We expect this to improve the accuracy and performance for panoptic driving perception tasks. The potential benefits include enhanced driving detection, drivable area segmentation, and lane detection. We will also discuss the novel aspects and challenges of our project. Moving on to the existing research, as you can see in the diagram above, in the diagram shown, there's a backbone, there's a neck connected to the backbone, the multitask learning outputs as presented as drivable area segment head, detect head, and lane line segment head. So the SPP, spatial pyramid pooling, brings along with it its own advantages like handling variables as inputs and reduced computation. But it also comes along with a few limitations as well, like the loss of spatial resolution. Hence, we sought to improve it by adding FPN to our architecture. Now, is it extending or differing from our research? We'll get to see that later. Moving on to the dataset. In this project, we have actually used the BDD 100,000 dataset, which is a comprehensive dataset designed for various driving perception tasks. The dataset format is similar to the COCO dataset, which is a widely used dataset for object detection and segmentation tasks. The BDD 100K dataset is divided basically into three parts: 70,000 images for training, 10,000 for validation, and 20,000 images for testing. This division allows us to train our model effectively and access its performances on unseen data. The dataset offers a diversity in terms of scenes, including both at daytime and nighttime frames. This diversity helps a model to learn to detect objects in various lighting conditions at different times of the day. In our project, we use this dataset to evaluate our model based on the feature pyramid network with panoptic segmentation. The dataset provided us with the necessary data to develop an effective solution for traffic object detection, contributing to the advancement of autonomous driving systems. Let's move on to challenges. Despite its advantages, this dataset has certain limitations. Even if we have a diversity in different daylight conditions, one issue is that lack of diversity in certain aspects like weather conditions and geographical location, which might not be the representative of all the real world scenarios. But this lack of diversity can lead to overfitting, where the model performs well on the training data, but fails to generalize new unseen data. To mitigate this risk, we implemented data augmentation techniques such as random cropping and flipping. Another challenge is the class imbalance in this dataset, where some object classes are underrepresented. This imbalance can negatively impact the model performance, as it may struggle to detect less frequent objects. Now, to address this issue, we use class balance samplings, which ensures equal representation of all the object classes during training. This approach helped to improve the class distribution and overall performance of our model, allowing it to effectively tackle the challenges faced in the traffic object detection.
So in this slide, we'll talk about the feature pyramid network and why we chose this particular algorithm for our project. The first reason is the hierarchical feature learning. The FPN is able to capture multiple features at multiple scales, and that allows us for robust feature representation. And this is able to capture both the high level and the low level details. The second reason is the multi-scale object detection. Uh, the FPN is able to detect the objects of various sizes, and thus it's particularly valuable for traffic object detection tasks where the object sizes can differ significantly. The third and the most important reason is the improved accuracy and performance. The FPN is able to enhance the performance of various state-of-the-art models, and it makes the solution uh, very impressive. To summarize, the FPN's capabilities makes us makes it a fitting choice for our project as as it is able to address the traffic object detection challenges and also improve our model's performance. Moving on to the methodology. For the project, we use the BDD 100K dataset, as my friend Aditya has just explained. The dataset consists of total of 9 major classes. To prioritize these classes, we predefined weights and then we integrated them into the pyramid structure. We decided to ignore the lower 3 classes, which include trees, buildings, and miscellaneous structures. This was mainly due to the high training time. So instead, we focus on the remaining 6 classes, which can be grouped into 2 categories: the primary classes, which consists of vehicles, lane lines, and drivable areas, and the secondary classes, which includes the footpath, pedestrians, and traffic signals. For uh, for each of the detection head, we had specific configurations that was tailored to the primary classes. Our model was able to catch and properly segment all 6 classes, but we only masked the primary 3 for the purpose of our results. Compared to the existing result that uses YOLO-P with a neck head setup, we can see here that we have decentralized the model and we have removed the SPP and we have implemented our FPN. This approach allows us to compare our model with the conventional setup. For the loss function, we employed the weighted binary cross entropy and the mean square error for different parts of the model. The detect head used the WBCE, while the drivable area segment head and the lane segment head both use a combination of these two loss functions. These loss functions were chosen to optimize our model's performance in detecting and segmenting the selected classes, and this contributed to the overall effectiveness. Moving ahead with the model selection, we had 3 different model choices. The first was the ResNet 50, the second ResNet 101, and the ResNext. All these 3 are very popular for self-driving cars, and thus we decided to move on with these 3. We compared the mean IOUs over 5 iterations and the speed in FPS. Uh, Based on our testing, we found that while the 3 of them have similar IOUs, the ResNet 50 gave us a pretty high speed. So we decided to move ahead with ResNet 50 because speed is our primary focus here. Talking about uh, the architecture of the ResNet 50 model, the ResNet 50 model has various layers. The first layer is the convolutional 1 layer, which is the 7x7 layer with the stride of 2. This layer is followed by Bayes normalization and the ReLU activation function. Convolution 1 layer is followed by max spool and 4 different layers. Each of these 4 layers consists of 2 residual blocks and a different number of filters that start from 64, 128 to 56, and the last layer has 512 filters. We can note here that uh, each of these 4 layers consist of 2 convolutional layers, and each of them is followed by Bayes normalization and ReLU activation. We also added a skip connection that sums both the input and the outputs of the block.
So now taking on from where Anshul left here. So now after we decided we were confirmed with the model which we were going for our FPN network, that is the ResNet 50. The next step which comes in the way is selecting the hyperparameters and tuning them. So initially, out of all the hyperparameters, we decided to go with 3 major ones, which we were going to alter and change and iterate to actually tune the network, which were learning rate, batch size, and epochs. In the case of we decided to go with simpler values for them, so in order to get an easier tuning period. For example, we decided to go with batch sizes like 8, 16, and 32, which are pretty standard for the industry. And like epoch numbers were like taken as 50 or 100. Using these, we were able to tune a set of iterations which helped us to decide the best of all and go ahead with the hyperparameter tuning. Regarding the metrics, we decided to go with three important ones. That is accuracy, speed, that is in FPS or frames per second, and IOU, that is intersection over union. To select the best hyperparameters, we used a weighted cumulative metric, which combined the scores of these three individual metrics based on our requirements from the network. For example, our weighted cumulative metric as calculated here shows that W1 times accuracy plus W2 times speed plus W3 times IOU, where W1 and W2 are both 0.3 and W3 is 0.4 based on our requirements. As we wanted more, we gave more importance to the IOU as compared to the accuracy and speed for our output using the FPN network. And this is how we were able to optimize the model's performance and find the most suitable hyperparameters as shown in the table below, where we have all the iterations, and the highlighted yellow set of hyperparameters were the ones which we found performing the best for our network. Now, coming on to the results, we were able to visualize on tuning the three different segmentations and object detections as shown here. Initially, we first the visualization for the lane line segmentation is shown here. On the we decided to go with daytime and nighttime results because we wanted to make sure that the results were pretty much aligned and accurate and streamlined over any type of input given to the system. So that's why we decided to go with daytime and nighttime. And here we have the drivable era segmentation again in daytime and nighttime. Going forward with object detection and localization, which we again did for the daytime and nighttime. Thank you.
So now we finally get to see the full capabilities of this model. First up is an input video showing a generic environment a car would be expected to travel in. On the next slide, the model, through the use of FPN, is used to successfully detect the lanes, drivable areas, and instances of different cars simultaneously at roughly 24 FPS. Next, we have the results. So we've compared the two setups, YOLO-P with spatial pyramid pooling and YOLO-P with FPN, the former being the existing work and the latter being our implementation. In terms of accuracy, the existing YOLO-P with SPP was at 70.5%, whereas YOLO-P with FPN reached only 66.1%. For speed measured in FPS, the existing YOLO-P achieved 41.35 FPS, whereas our YOLO-P with FPN reached 24.7. Lastly, for intersection over union, the existing YOLO-P with SPP achieved 26.2, while our YOLO-P with FPN slightly outperformed it with 26.47. These results show that our approach, while having slightly lower accuracy and speed, do demonstrate an improved IOU, highlighting the potential of FPN integration in the YOLO-P architecture. Fine, now we come to the conclusion. So we've presented our work on implementing the FPN with panoptic segmentation for traffic object detection in this presentation. We have utilized multitask learning to enable our model to perform multiple tasks simultaneously, such as object detection, drivable area segmentation, and lane detection. To address the dataset challenges such as lack of diversity and class imbalance, we've employed data augmentation techniques and class balance sampling. We also carefully selected hyperparameters using a weighted cumulative metric to optimize our model's performance. Our results show that our approach has a comparable IOU performance, highlighting its potential for traffic object detection tasks. Overall, our research contributes to the development of advanced autonomous driving systems, paving the way for future research and application in the field of autonomous driving and object detection. Thank you.